My name is Votipka. I'm a PhD student at the University of Maryland, and in this video, I'm going to talk about the work my colleagues and I in the Security Privacy People Lab did building and validating a scale for secure software development self-efficacy. Producing secure software is important, and developers play a critical role. Unfortunately, we still see several solved vulnerabilities. These are bugs attackers can use to malicious ends, crop up in real software. These are vulnerabilities that have a known solution, either an API, language, or best practice a developer could have used to prevent them. This chart shows the number of vulnerabilities reported each year. Each line signifies a different type of vulnerability as classified by NIST's Common Weakness Enumeration categorization. Note that buffer errors still remain in the top two spot. Information leak disclosure and proper access control and cryptography issues have barely or not at all decreased. And yet, they're supposed to be relatively solved issues given current libraries and APIs. Why are we still seeing these vulnerabilities in the real world? Well, one reason is that security is really complicated. NIST's National Initiative for Cybersecurity Information, or NICE, Cybersecurity Education, or NICE, framework identifies 44 unique tasks a developer must perform to ensure their software is secure. This list here shows just a sample of that, and you can see sort of the complexity inherent in this challenge. And unfortunately, prior work has shown that many developers do not believe they are qualified to perform these tasks. In fact, other prior research has shown this to be the case when they actually had developers either trying to write secure code or trying to find vulnerabilities in insecure code. So how do we help developers write more secure code? Well, there are several different methods currently in use. One is teaching them through active practice and other educational tools. There are also several guidelines outlining the considerations developers need to make when thinking about security. And finally, there are analysis tools that developers can use to alert them when they might be doing something wrong, and APIs to handle complex security concepts for them. But do these actually improve secure development practice? How do you actually measure skill improvement in this domain? Many prior studies have used secure development assessments where participants are given a small requirement specification and asked to write a secure program or try to find a vulnerability in known insecure code. Unfortunately, this can take a large amount of time for participants to complete and does not scale well. We propose an alternative approach to measuring secure development skill, specifically a validated psychometric scale. Human behavior researchers rarely develop scales to measure elusive phenomena that cannot be observed directly due to cost or complexity. Specifically, we propose measuring developers' secure development self-efficacy, or their belief in their ability to write secure code, which correlates with actual skill in several other contexts outside of secure development. Now, this scale would measure developers' belief in their ability to complete secure development tasks, such as identifying security problems during software design or employing secure programming languages. We refer to this scale as SSD-SES for short. So to develop a scale, we followed Nedemeyer's four-step process. We began with construct definition and defining the content domain, and here we tried to clearly identify the targeted construct scope, the sort of underlying idea, and we were focused specifically on tasks related to secure production or code production. So this meant we were focusing first on only development tasks, nothing related to deployment or maintenance or operations, only in that first phase. And we also were only looking at sort of common tasks, things prescribed by widely accepted secure development frameworks or experienced security experts. Next, we tried to generate and judge a set of items, sort of an initial pool of candidate questions. And then we wanted to ensure that they were relevant to the construct, that scope that we defined previously, and that they were understandable by our developers. And for the first part of this, for the item generation, we looked at 5 of the most popular secure development frameworks, all given here. And for each, 2 researchers independently reviewed each framework and all the tasks identified or described by them. And we identified 57 unique tasks from these 5 frameworks. Then we took those 57 tasks and we presented them to a set of 22 security experts who had on average 20 years of experience. And here we wanted them to rate in a survey each item's appropriateness to that specific content definition that we identified previously. And the goal here was to identify content validity to make sure that those tasks were associated with that construct that we're trying to measure. And we also allowed them to suggest additional items. So after this phase, we ended up with a total of 58 remaining items. Some were removed, some were added. And then we took those to a set of 8 professional software developers, and we had them actually go through each task, reading and sort of thinking aloud as they went through in front of the researchers, so that we could get an idea of how they were thinking and whether or not there was any kind of confusion with the wording, so we could get an idea of face validity. And after this phase, we actually changed the wording of a few of the questions, but we maintained the same set of 58 items. Then we moved into the developing and refining the scale phase, where we were using exploratory factor analysis to identify the underlying factor structure or the subcomponents of the targeted construct. We also wanted to refine the item set to its most efficient form, so that it only included items or tasks with sufficient variance among respondents, and also so that it maintained reliability, so that the scale was consistent or consistently measured these constructs across runs of or people taking the actual survey. So first we began with a survey of 157 software developers. These were recruited through freelancing services, Prolific, as well as just through forums related to software development. And each participant was asked to rate on a 5-point Likert scale each of the 58 items and their confidence in their ability to perform each task, from I'm absolutely confident to I'm not confident at all. We also gave them the option to state that they didn't understand the option. And so based on these responses, we first checked for a low item total correlation, so to see if there were any items that maybe appeared to not be measuring the same thing as the other items and not really be related to the construct. We also looked for any ceiling or floor effects, which would indicate that we might not be measuring the actual construct because it's either all the responses are on one end of the scale or the other. We didn't see any of these effects with any of our items. We also looked for whether or not participants, and a large portion of the participants responded that they didn't understand the questions, and there were 13 items that had greater than 5% of participants, since we removed those from the pool of items. With the remaining items, we performed a principal component analysis. From this, we found that there were 2 remaining factors. And so for those sort of underlying factors that made up SSD-SES, we then wanted to figure out which items were associated specifically with each of those factors uniquely. And so we only retained items that met these 3 criteria, that they loaded at least 0.5 on one of the factors, that the item loading on the primary factor, so the one that had the highest loading on, exceeded 2 times the other factors, and that the item's communality was greater than 0.4, and this is just the variance accounted for by all the retained factors. And these 3 criteria basically just tell us, basically allow us to make sure that our items that are remain specifically measure a single underlying factor, and so that if we see a change in one of the item responses, we know that that's a change in that underlying factor, and it's not sort of noise shared across the 2. And this left us with retaining 18 items from our total 58. And then we also tested internal reliability and item total correlation of the remaining items, both together as the full scale and then for each subscale, and found that it had a reasonable level of reliability and item total correlation. So to finalize the scale, we wanted to confirm that the previously identified factor structure held after we ran it with a new population, and that it still had maintained sort of those reliability measures that we wanted to make sure or check for. And so we did another survey with 146 software developers, and again we had all the participants respond with their level of confidence performing those 18 tasks on a Likert scale, on the same Likert scale. We removed the do not understand option. We also had them respond. Each participant was shown 2 of the following 6 additional psychometric scales. First, we included the computer programming self-efficacy scale. This is included for convergent validity. And the idea here is that we wanted to make sure we expected that people's ability to write code was associated with their ability to write secure code. And so we wanted to see if this relationship held up. We also wanted to test for divergent validity to make sure that we're actually measuring something different. So here we looked at 2 scales related to end user security behaviors, beliefs, as well as for just general self-efficacy. We also included 2 psychometric measures related to sort of personality factors, the need for cognition, which is associated with someone's curiosity or their want to perform tasks that require cognitive or them to think, basically, and also their general decision-making scale, which measures how people go about making decisions and has several different subscales related to different decision-making styles. And so for this, we repeated our PCA on those 147 responses, and we actually found that 3 of the items either switched factors or didn't sufficiently load in the second round, so we removed those because those didn't hold up over multiple rounds. But the remaining factors still met all of our criteria. We also performed a confirmatory factor analysis, which utilized several different goodness of fit metrics that are given in the paper, and we found that it met all the requirements for these sort of goodness of fit tests. And so this left us with the following 15 items broken into these 2 factors, and these were generally aligned with the first being participants' ability to find and fix vulnerabilities, so that specific skill, and then also their ability to communicate security concepts to others. Then when we compared it to the other scales, we found that our SSDs correlated with the computer programming self-efficacy scale for both of our subscales. So this is kind of what we expected. We also didn't see any correlation with any of the other scales that we included for discriminant validity checks, which is again what we expected. We also saw that specifically the vulnerability identification and mitigation subscale did correlate with the need for cognition scale. And this suggests that developers who are more curious are more likely to feel confident in their ability to search for, identify, and mitigate vulnerabilities. This corroborates prior work which observed developers who were more open or curious were more likely to find vulnerabilities in secure development puzzles. So, stepping back, now that we have this validated scale, how can we actually use it? Well, one that we sort of talked about as we were motivating the development of the scale is that we can use it for testing educational interventions. You can use it as a pre and post to see which might be most effective and see how students respond to those. It can also be used as a covariate to approximate secure development skill. So for example, in a usability study of security APIs, it would be beneficial to include SSDs as a covariate to ensure differences in outcomes between participants occur because of changes to the API and not differences in security skill. Finally, you could also use it to measure secure development culture. So a manager could survey their developers to identify who might most benefit from additional security education. So in summary, we've developed SSDs, which is a 15-item scale that can be divided into 2 factors related to vulnerability identification, mitigation, and secure communication. And it was developed and validated through review of 5 of the most popular security development frameworks, surveys of security experts, and several software developers. And we've also given several things that it could be used for. If you have any questions about this research, in general, how SSDs can be used or how we went about this, happy to answer those. I've given my contact information at the top right corner of the slide. Also, if you're just interested in our research generally, definitely check out our website, secprofessionals.cs.umd.edu. With that, thank you for your time and interest in watching this video and in your interest in our work. Thanks.